This is a revision video for Chemistry CP4 for Year 9, based around the new Edexcel GCSE 2016 for your CP4 exam coming at the beginning of the year. So the first thing you need to know about is the atom. Everything in the world around us is made of atoms. They're the building blocks of matter. Atoms made up of three particles called protons, neutrons, and electrons. You know the charges: electron being negative, proton being positive, neutron being neutral. Got those there as well. You know the masses: proton is 1, neutron is 1, electron is 0. So the electrons are around the outside in shells, around that tiny nucleus, which is very small compared to the rest of the size of the atom. And the atoms are an atom of a given element will have the same number of protons in the nucleus, and this is unique to that element. So carbon will always have 6 protons, and nitrogen will always have 7 protons. You change the number of protons, you change the element. Atoms contain the same number of protons and electrons, so there's no overall charge. So you can see that this atom here has 2 protons, so therefore it has 2 electrons. Know these definitions. So atomic number is the number of protons, mass number is the number of protons and neutrons, and the relative atomic mass is the mass of an atom compared to that of an atom of carbon 12. If you have 2 atoms of the same number of protons but a different number of neutrons, they're called isotopes. So isotopes have the same number of protons but a different number of neutrons. All these highlighted bits are key. Different isotopes have the same atomic number, the same number of protons, but different mass number, number of protons and neutrons. This means the relative atomic mass of some elements are not whole numbers. So you have chlorine, for an example, which is a relative atomic mass of 35.5. So you can calculate the relative atomic mass of an element from the relative masses and abundances of its isotopes. So you have chlorine, which is a relative mass of 35, and there's 3 of those, and there's chlorine with a relative mass of 37, and there's 1 of those. That's 3 to 5, so there's 3 of those to every 5 of these. You do 35 times 3, and you do 37 times 1, and you add the 2 answers of those together. So whatever answers you get for both of those, you add them together. You then divide them by however much there are all together. So it's 4 in this situation. So you add that times that to that times that, and divide it by those 2 numbers together. So that's 4. What you find from that is you end up with this number here, 35.5. So that means that it's just not going to come out as a round number. It doesn't normally come out as easy decimals either. Okay, so normally you round up to the nearest 0.5. So the periodic table was essentially put together by Dmitry Mendeleev. Right. So he published a periodic table, and he arranged the elements known at the time in order of relative atomic mass. So that's the mass of an atom compared to carbon 12, as I mentioned before. He realized that the physical and chemical properties of elements were similar to their atomic mass in a periodic way. So he arranged them in a group, and he realized that similar properties fell into similar vertical columns. So you've got similar properties in the same column as each other, in the same group. Sometimes this method of arranging elements meant that there were gaps, like over here in group 3. So instead of seeing this as a problem, he thought, you know what, we just haven't found that element yet. So he was able to work out the atomic mass of the missing elements and predict their properties before they were even discovered. So when they were discovered and he was proved right, a lot of scientists started to believe what he was saying. He predicted up to 3 elements quite easily and quite quickly, and their properties. And so the modern formula periodic table is shown over here. On the left hand side of the table we have the metals and the centre part there, while on the right hand side are the non-metals. So these ones are the non-metals. Elements are arranged in order of increasing atomic number now, and the rows are called periods. So it's periods going this way, periods going this way, periods going this way, and groups going this way. Periods across and rows going down. Sorry, and groups going down. Periods across and groups going down, sorry. Right, so you need to know a bit about electron configuration. The first shell of an atom can take up to 2 electrons, and every shell after that can take 8. Okay, so if you've got 10 electrons, you put 2 in the first shell and 8 in the second. And remember, you can lay it out in this way. So you can see over here, you've got fluorine, which has 2 and 7. 2 electrons in the first shell and 7 in the one after that. The interesting fact you get from this is the number of electrons in the outer shell tells you the group, so it's got 7 in the outer shell, it's in group 7, and the number of shells tells you the period, so there's 2 in that means it's in period 2. So you've got calcium over here, 2 in the outer shell, group 2, you've got 1, 2, 3, 4 shells, it's in period 4, and there's calcium, group 2, period 4. So it works perfectly. So the electron configuration is important in the idea of bonding, and that's what we move on to next. Ionic bonding and covalent bonding. That is when atoms come together to try to get a full shell of electrons. So ionic bonding is formed by the transfer of electrons to produce cations and anions. You don't really need to know that phrase there. So ions are charged atoms. They produce, they're produced when atoms gain or lose electrons. Okay, so ionic bonding, an example of that is salt. So you can see over here, sodium originally has 1 electron in its outer shell. It loses that 1 electron, so now it's positive. Chlorine has 7 electrons in its outer shell. It gains 1 electron, so it's now negative. Okay, this electron's been lost, it's been gained over here. These two will now attract. We've also got magnesium oxide, which has 1, 2 in its outer shell, so if it loses those 2, it becomes positive 2. And you can see oxygen here has gained 2 electrons. Okay, so it's gained 1 there and there. There's one that's gained, and there's the other one that's gained. Therefore, it's negative 2 because it's gained 2 electrons. So ionic compounds have this lattice structure, so it's like a repeating pattern, a regular arrangement held together by strong electrostatic forces. So what that means is that a large amount of energy is required to break these bonds, but it also means that they conduct electricity. So a large amount of energy means they have high melting points and high boiling points. Okay, they can only conduct electricity when they're in an aqueous state, so they're dissolved in water or when they're molten. This is because when they're in this aqueous state or when they're molten, the ions can move around and they can carry the current. Another type of bonding is covalent bonding. So this is where they share electrons now. So previously the electrons were transferring, now they're actually sharing. Okay. So what simple molecular covalent compounds here. So hydrogen has 1 electron in its outer shell. It wants 2, so it shares with another hydrogen to end up with those 2. Hydrogen has 1 and it wants 1 more, so it shares with chlorine to get its 1 more. Chlorine has 7 and wants 1 more, so it shares that one with hydrogen to end up with a full outer shell. Here's a trickier one. So methane, well, the carbon has 4 and it wants 4 more, so it shares 1 with every hydrogen. So that hydrogen gives that 1 to it, so therefore each hydrogen now has 2, but each carbon has 8 altogether. Similarly, oxygen has 1, 2, 3, 4, 5, 6 in its outer shell, so it needs 2. Shares it with another oxygen, so they both end up with 8. Oxygen has 6, needs 2 more. Shares with hydrogen, H2O. Carbon dioxide has 4. Carbon has 4, needs 4 more. Shares with oxygen, ends up with carbon dioxide. So both the oxygen have 8 and the carbon have 8 now. So there are 2 main types of covalent substances, simple molecular and giant molecular. These are all simple molecular. They have low melting points and low boiling points. Even though there are strong forces between the carbon and oxygen, between each carbon dioxide atom, so this one, and another carbon dioxide that might be over here, there are weak forces between them. So they can break apart very easily. They're weak intermolecular forces, weak forces in between the molecules, so that they can become gas very easily. This means that they are poor conductors because they don't have any ions, and that's why they're normally liquids or gases. Or if not, they're easily meltable solids. However, if covalent compounds have this giant repeating structure, they can change their properties. So giant covalent structures have a lot of non-metal atoms which have been joined to adjacent atoms by covalent bonds. They're usually extremely strong because there's many bonds involved. So over here we have graphite, and over here we have diamond. Substances with giant covalent structures have very high melting points because they have a lot of strong covalent bonds. Graphite, melting point of 3,600 degrees Celsius. Diamond doesn't conduct electricity. Graphite has free electrons, so it does conduct electricity. So across these layers, graphite can actually conduct electricity. Graphene is single layers of graphite. Graphite is formed from carbon, in which the carbon atoms form layers. These layers slide over each other, so it's very much softer than diamond. It can be used as a lubricant actually. That's why it's used in pencils, because every time you write, these layers are coming off. Each carbon atom in a layer is only joined to 3 others. And that's why it has that free electron, which can therefore allow the conduction of electricity. Diamond, each carbon atom there is joined to 4 others, so it has this giant covalent structure. As a result, it's very hard and has a high melting point and doesn't conduct electricity. Polythene is a polymer that you might have come across that consists of large molecules containing chains of carbon atoms as part of ethane monomers. So that's another idea of a large amount of carbon atoms joined together. Sorry, excuse me. It's hay fever season. So, fullerenes. Fullerenes are a large class of allotropes of carbon, so all these are allotropes of carbon, and that are made of balls or cages or tubes of carbon atoms. So Buckminster fullerene is one type of fullerene. It has 60 carbon atoms and arranged in a hollow sphere, like other substances that are giant molecular structures that have high melting points and high boiling points. And that is the end of your chemistry video for CP4 in year 9 about the new GCSE in science.